Hello, everyone. This is Elisa Baum. I am GridGain Systems Director of Product Marketing. We'll begin in just a moment, but first I need to conduct just a bit of housekeeping. Could you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me? And let's see, I see hands. Great, thank you very much. Next, during the webinar, you will be on mute, but should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on GridGain's blog. In addition, a recording of this webinar will be made available to everybody within 48 hours, and I'll also send links to the slides. I would like to thank you for attending today's webinar, GridGain 8.1 and Apache Ignite in memory performance with the durability of disk across thousands of servers. It's being presented today by Dmitriy Setrakyan, who is GridGain Systems Chief Product Officer. And with that said, I will turn the floor over to him. Go ahead, Dmitry.
Hello, everyone. Thanks, Alyssa. Just a quick intro again. I'm Dmitriy Setrakyan. I am one of the founders of GridGain, and I'm also a PMC member of Apache Ignite. I've been probably doing this in the industry for past maybe 20 years. For the past 10 years, I've been focused on distributed systems, and most of my life I've been coding and architecting clusters, multi-threaded components, etc. So I love distributed systems. I know quite a bit about them, so hopefully we'll keep it fun and entertaining. So a bit of agenda. So we will briefly talk. We have a lot to cover, so I'll be going somewhat fast. We'll quickly define what GridGain and Ignite is. We will look at key components. We'll look at features, how the different storage systems compare, and where does Ignite belong on a CAP theorem? That's a never-ending question. And then we'll switch and talk in detail about the new durable memory component in Ignite, which is essentially memory that has persistence component to it. And we'll talk about how it's a page-based memory, so we'll talk about page-based memory architecture, how B trees are structured, how free lists are structured, how persistence works, how write-ahead logs works, etc. And then we'll move to a Q&A session. All right, so just before I start, I just want to mention that with GridGain 8.1 and which has been released, and Ignite 2.1, which will be released in 2 weeks, give or take, maybe 2 to 3 weeks. We've moved from being a purely in-memory product to a memory-centric architecture. And I'll define what that means, and we'll talk about what that means. But first, let's define what GridGain and Ignite is. So Ignite is a memory-centric platform that combines a distributed SQL database together with a key value data grid in one platform. It is asset compliant, it is fully transactional, it is always available and horizontally scalable. So if you think about storage systems and how storage systems have evolved historically, then you'll see that we started out from traditional RDBMS systems, which are monolithic databases, generally deployed on larger servers, and usually are not a scalable architecture. So essentially, they support failover. So if one crashes, another can take over, but they're not scalable. You cannot scale. You cannot keep adding more servers and distribute load between those servers. It's usually so they usually support failover. So about mid of 2000, like about 2005-ish, that time frame, we start the NoSQL databases started coming up, and essentially the premise was that we are going to add scalability and availability, but we are going to sacrifice consistency because pretty much whenever you hear NoSQL, you should immediately think that transactions are not supported. So the databases are eventually consistent. So for a while, whenever we thought about distributed databases and distributed storage systems, we thought that, especially the ones that support that are persistent, that are durable, we immediately thought no transactions. So that's what we're changing with Ignite. Ignite actually is a distributed, durable, and transactional system that supports both SQL and SQL syntax. You can talk to Ignite using free-form SQL and a key value API. So again, it's the combination of durable, distributed, and consistent that makes Ignite offering fairly unique, fairly unique technology. So let's take a look at some of the features that are some of the key features available in Ignite. It's non-exhaustive list by any means. So as I mentioned, Ignite has a distributed database component, distributed SQL database component. So what does it mean? You can talk to Ignite using exclusively SQL. So you can actually connect to Ignite using, just like you would to any database, using either JDBC or ODBC driver. And you can actually start issuing inserts, updates, select statements. So you can populate your data using SQL. You can create a model using SQL, create the schema. So you can create tables, drop tables, etc. So Ignite fully supports SQL, DDL, and DML syntax. It is ANSI compliant, and as a database, it is distributed. It works both in memory and on disk, and one of the distinguishing features here is that it supports transactions. So unlike most of the distributed systems out there, if you think Mongo, Cassandra, Couch, probably missing some, but unlike most of the distributed systems, Ignite does support transactions. Another cool feature that our distributed SQL database supports is distributed joins. Joins are not easy to implement, and especially in a distributed systems, how do you actually manage joining on different keys, especially if they reside on different servers? So we definitely prefer that whenever you do joins, there's as little distribution as possible. So we support both collocated, what we call collocated and not collocated joins. Collocated joins are joins on the keys that reside on the same server. So you can have a distributed system with many keys spread out across many servers, but if you do a join in such a way that the keys you are joining on are located on the same server, then the joins will work faster. If not, then they will work slower. So you should always strive, you should always try to collocate your data in such a way that the queries will perform better. And we actually give users full control on how to collocate. For example, you can have many companies, company objects, or company rows, if you will, stored in your system, and many employees that work for those companies. But you can collocate employees with the companies they work for. So essentially, in this case, a collocation key would be a company ID. And if you do that, you can easily join an employee table with a company table and get all the employees that work for the same company and do any kind of aggregations, averages, what's not, group bys on them, etc. If you can't collocate, the query will still work, but now we have to move data sets around, and that is very slow. So if you cannot collocate at all, maybe you should not be doing joins, or maybe Ignite is not, a distributed database actually maybe is not the right product for you. And we also have re-architected our indexing with this new release, where now our indexing is fully based on B+ trees, which work on top of our page-based memory. They work either in off-heap memory or on disk. So essentially, it doesn't matter to us where B tree index is. Ignite will still use it and utilize it. Of course, the more you can fit in memory, the faster it will work. But there's no requirement that your whole index must fit in memory. It can be partially in memory, partially on disk. All right. As I forgot to mention actually, that we also support two replication schemas. One is full replication, and another one is partitioned. And here's how it looks. Essentially, on the right you have a partitioned replication. On the left you have full replication. The arrows here show how the data is moved around and how like whenever you access it. If you access it on a server, then the data that is local to that server will be accessed directly. If it's not local to that server, it will be fetched from another server and still made available to your process. If you're on a client utilizing a near cache, then the data comes from a cache. If not, it's fetched from a server that has the data. So in a partition cache, you can configure as many backups as you want. But in a pure scenario, you have each server responsible for a certain set of partitions. And keys belong, so the relationship goes this way. Keys belong to partitions, partitions belong to nodes, to servers. So each server has a responsibility for a certain set of primary partitions. And if you have backups configured, then it will also take over responsibility for backups, a certain number of backups as well. So you can have maybe one redundant copy, which is backups equal to 1, 2, 3, etc. So full replication is a edge case of a partition replication where number of backups is equal to number of nodes. So in this case, every server absolutely has all the data. So full replication obviously is expensive for updates. Every time you change anything, change a key value pair, you have to replicate it across all the nodes in the cluster. You have 5 nodes, it goes to 5 nodes. You have 1,000 nodes, now you have to send an update to all 1,000 nodes. In partition case, you only update the primary copy and whatever number of backup copies you have. So so partition replication scales horizontally much better. However, full replication is more available because the data is available on every server. So you can mix and match how you between data sets. You can have some data sets that are fully replicated, some data sets that are partitioned, maybe like, let's say 100 replicated, 30 partition data set would be a typical scenario for Ignite, for example. And then you can do issue queries and joins between these data sets. So again, join between a partition and replicated data sets will always work because replicated data sets are available on every node, and hence collocation is always 100%. Because whenever you join a partition data set with a replicated data set, the data is available on every node at all time. If you join partition dataset with another partition dataset, then you have to worry about collocating the keys you're joining on, as I mentioned before. So these are the replication schemes supported in Ignite. Another key component, a key feature available in Ignite is a data grid. And if you look traditionally at the storage systems, then they usually support one way to talk to the data. If it's an SQL database, then you can talk to it using SQL. If it's a key value storage, then you can talk to it using key value API. Maybe you can, if it's a MapReduce system, you can talk to it using MapReduce API. However, rarely you will see when a system will allow you to use more than one API to talk to its data. In Ignite, we actually support multiple ways to talk to the data. So as I mentioned, SQL is one way that you can interact with your data. A key value store would be a key value API, and would be another way you can interact with your data. So a key value data grid is essentially represents an in-memory key value store that also has persistent capability. So you can actually interact with any data stored in Ignite using key value data grid API. For example, let's say you inserted data into Ignite using SQL insert statement. Maybe you manipulated it using update statements, and then you can get it using either select, or maybe if you prefer, you can get it by key via key value API. And vice versa too. You can update using key value API as well. Of course, data grid is also ACID compliant as everything else in Ignite. And one of the distinguishing advantages of supporting a key value API is allowing for collocated processing. If you think about how traditional systems work, then you generally are dealing with a client-server processing. You are fetching data from server to the client, and you process it on the client side. Fetching data and moving data around is very expensive, and when you do it a lot, you essentially can kill any type of scalability in your system. Kill network, you can kill performance, etc. However, in collocated processing paradigm, you're moving computations to the data. You don't move data to the computation. Of course, you can still move data to compute. You can still support the client server paradigm, but it's generally recommended that you move compute to the data, not data to the compute. So collocated processing allows you to send a piece of logic, a function, or a lambda to the server where the data resides and process it directly on that server. So there would be no data movement. All the data access will be local and hence very fast. And that's one of the key characteristics of a in-memory or memory-centric system. It's to allow to process data exactly where it resides, collocated processing. And of course, DataGrid traditionally supports persistence by integrating with other persistent stores, like other databases. So DataGrids can very well integrate with traditional RDBMS systems, or like Oracle, Postgres, or any type of database, Cassandra, Mongo. You can, and essentially, DataGrid can serve as a distributed caching layer on top of any existing persistent system. Now with GridGain 8.1 and Ignite 2.1, DataGrid will also work with Ignite native persistence. So you can actually store data directly in Ignite and without having to, and persist it in Ignite without having to offload it to any third-party system. However, why is integration with a third-party persistent systems is important? My reason is that data is usually sacred in most of the enterprises, and think about it. If an enterprise is deciding to move into a distributed architecture, it's a huge paradigm shift for all the, not only technical paradigm shift, it's a paradigm shift for all the engineers, all the employees that work on that system. So it's so doing it in one rip and replace fashion would be very risky and very expensive. So it's much easier to keep your data safe, keep your data as is. Not like, because probably there are many systems within your organization that learn how to talk to the data, talk to your database in a way that your database was created. So it's usually safer to leave database untouched, but add scalability by adding a distributed data grid, distributed memory cache, memory store layer on top of that database. And add scalability, add in-memory processing, add performance to your system, and then maybe as a phase 2 down the road, if you decide that you actually can start replacing your database as well, you can start gradually switching to Ignite persistence. So again, this type of integration enables you to slide in Ignite gradually into your architecture without having to rip and replace your existing database, your existing storage. So Ignite, so these two, like a distributed SQL database and a key value data grid, are key components in Ignite, and essentially what makes an Ignite offering fairly unique. It's distributed, in memory, memory-centric, distributed, durable, and consistent, fully transactional system. Again, I've probably use these terms quite extensively. What is memory-centric? What is disk-centric? If we define memory-centric, then both memory-centric and disk-centric systems are durable. So they both support persistence. They both can outlive system crashes. However, memory is used differently in the systems. In a memory-centric system, memory is not used as a you can use memory as a primary store of your data. If you think about disk-centric system, like a traditional database, let's take Oracle, Postgres, MySQL, etc. All of them utilize memory. All of them do caching. All of them will serve data out of memory if it was cached there before. So they utilize memory as a caching layer for the data that is stored on disk. However, a memory-centric system uses memory as can use memory as a primary store of the data. So memory is actually not just a caching layer; it's a storage. It's a transactional storage. It's a storage that supports SQL, etc. Memory-centric system can actually turn off persistence altogether and use memory as its primary store and serve data directly out of memory. In case of Ignite, that would make Ignite probably distributed. If you turn off persistence, it would become a distributed in-memory SQL database, not just an SQL database. And on top of that, on top of supporting using memory as a storage system, memory-centric systems support collocated processing. You're allowed to process your data, process your computations directly on the nodes where the data resides. You essentially, all the processing happens in memory. Most of the data hopefully will be served out of memory, out of a memory store, and the data is processed in a collocated fashion. So there's no data movement. If you properly configure your collocation, there's no data movement here. All the data remains still, and only the computations travel to the data. Contrasted to the traditional database systems, NoSQL or RDBMS systems, where you actually have to keep bringing data from a server to the client. So it's a client-server type of paradigm, client-server type of processing, which is essentially more expensive and doesn't take advantage of all the distribution and all the data affinity in your system. So again, memory-centric essentially uses memory as one of the primary storages of the data and does support collocated processing. In this case, memory is just a caching layer, and processing works in a client-server format. Which systems actually are available today on the market that can be defined as durable, which support persistence, distributed, and asset compliant. Of course, once we add asset, all the distributed NoSQL systems do not fit. Once we add distributed, all the traditional RDBMS systems do not fit. So there are actually not that many storage systems that fit into this category. And I'm probably missing some here, but the most obvious ones would be Apache Ignite. There's also a system called NuoDB. There's, of course, Google Spanner and CockroachDB, which is very close to the Google Spanner architecture. So Google Spanner is a cloud-based database. Out of these four, Ignite would qualify as a memory-centric system. NuoDB, it would be a stretch. It's kind of a memory-centric system, but the collocated processing is supported via SQL store procedures. Why I'm saying kind of, my preference is to write computations, write logic directly in Java, and compute directly in Java, and create as complex Java code as required by my application. Doing that in SQL is a little bit cumbersome in my view. But nevertheless, NuoDB does support store procedures, which are executed directly on the nodes where the data resides. Google Spanner and CockroachDB would fall into a traditional client-server system. First of all, there's no store procedure support, and the data is generally accessed by bringing it to the client side and processing it on the client side. So again, these systems are durable, distributed, and asset compliant. So this, again, continuing that thought, let's take a look at all the properties of that are important for us in our storage when we store the data, and see which storages support different features and how they support them. If we look at RDBMS, traditional RDBMS, which is your essentially Oracle, MySQL, Postgres, DB2, etc. Those usually would be a monolithic deployment deployed in one server, probably a very large server because it has to store a lot of data and have a lot of processing power. However, those are not horizontally scalable systems. We can argue that they're vertically scalable because you can add more memory, you can add more disk, you can add more cores, and you can support larger data sets. However, vertical scale is not all that attractive. You do want to scale horizontally. You do want to add more servers, and you do want a highly or always available system. From availability standpoint, traditional RDBMS systems support failover only. They do not support horizontal scale like some NoSQL systems or Ignite would support. For example, Cassandra would scale very well horizontally. Mongo would scale horizontally. Traditional RDBMS systems would support failover. You can actually install another database as a full replica that will work either in active-active or active-passive form. But again, it's there only to support failover. It's not to improve scalability or to help with the processing of your workloads. And databases, of course, have strong consistency. They all support transactions. They all support memory and persistence. They work very well with caching memory. And most of them support SQL, key value, and they do not support key value or collocated processing. The collocated processing is actually doesn't even apply to traditional RDBMS systems because collocated processing implies some level of a distributed system. Then you have NoSQL, as I mentioned, that scales horizontally and is highly available at the expense of consistency. NoSQL systems generally do not support in-memory processing very well, and they're usually eventually consistent. And also there's another family of products that is called in-memory data grids or in-memory databases that generally would support horizontal scale, would be available and fully consistent, but they work only in memory. They're not durable. So an in-memory data grid or an in-memory database usually would not be able to cleanly survive cluster restarts, or usually they would have to preload most of the data in memory before they become operational. So memory is the superset of the data in a memory data grid or in memory database. Disk in a durable system, disk would be the superset of the data. So disk can store more data than there is available memory. So if you look at all these systems, then and combine them into one, then you would get Apache Ignite, in my view. It's a scalable system, available system, consistent, fully consistent, strong transactional support. Both can work both in memory and on disk, supports SQL and key value API and collocated processing. So that's where Ignite actually compares to most family of data storages that are known today. And of course, the most interesting question, how does Ignite fit into the CAP theorem? Just a quick overview what CAP theorem is. So CAP theorem has three components. It's consistency, availability, and network partition tolerance. So C for consistency, A for availability, and P for network partition tolerance. And the claim of the CAP theorem is that you can support only 2 out of 3. Your system can be either CA, consistent and available, CP, consistent and support partitioning, or available and support partitioning. But it cannot have all 3. It cannot be CAP, fully CAP. So where does Ignite fit here? I would say that Ignite is definitely a strongly CP system. It supports, it will never serve an inconsistent data. So in case of network partition, when the data cannot be served in a consistent fashion, Ignite would rather not serve data than provide you an inconsistent copy. So Ignite is definitely CP. I would also argue that Ignite is effectively CA, and so consistent and available. And the reason I would say effectively CA and not fully CA is because there are cases when Ignite may become unavailable due to network partitioning, for example, and if all the backups, for example, ended up in the lost partition, which is very unlikely. But network partitioning represents probably, if you look on the diagram on the right, the pie chart on the right, this is the graph of all the failures, network failures that were encountered in Google Spanner. If you look at network partitioning, it's only about 7 to 8%. About 50% of the failures are caused by user error, which will cause the user database to go down, but overall Google Spanner system will still be operational. And there are all sorts of other failures that are related to software bugs, to power outages, etc. And all these failures are not covered by CAP. So essentially, the way we're used to defining availability is in terms of how many nines, like 5 nines. What is the total time in a year that a system can be down. And if a system supports 5.9 availability, we say that it's generally available. And that's why I will say that Ignite is effectively CA, because the only time Ignite becomes unavailable is not, so Ignite can survive network partitioning if you define backups in memory. And if backups end up on different sides of the partition, your system remains available and all the data can still be served. And many of Ignite users do deploy it in such a way that in most probable partitioning cases, this is exactly what would happen, and Ignite would continue to be available. However, if you can't enforce that, and if that doesn't happen, if all the partitions end up in a lost segment, then yes, Ignite will become unavailable because it will never serve an inconsistent data. It would always err on the side of consistency. So again, because Ignite is almost always available, in most cases support 5.9 availability, Ignite would be effectively CA and definitely not AP, because we will never remove C. We will never remove consistency from this from Ignite. Ignite will always be consistent. So Ignite is definitely not AP. It will never prefer availability for consistency. It will always prefer consistency to availability. Okay. So now let's look at the new memory architecture. Let's actually have an architecture dive in. We'll talk about Ignite durable memory, how it works. We'll look at page-based memory architecture, and we'll dissect all the components that are involved here. So it's going to be very technical rest of the presentation. So what's a durable memory? Essentially, a durable memory is, think about durable memory as virtual memory with persistence. So it fully works in memory. As a matter of fact, Ignite fully re-architected its memory architecture to go from a key value based to a page-based architecture. And the primary storage went from on heap to off heap. Essentially, Ignite now will always work off heap unless you tell it that you want also to cache data on heap. That's required. That's almost never required. Off heap is usually fast enough. It removes all sorts of GC overhead and definitely is a preferable way to go. However, since Ignite is a durable memory, we also have to make sure that we support persistence and work very well with standard SSD and flash-based storages, and are again fully consistent on disk as well as in memory. So we introduce a notion of write-ahead lock and checkpointing and instantaneous restarts. So essentially, when a system crashes, Ignite can come back up without loading data in memory. It can become immediately available. So the data still will be on disk, but it will be lazily loaded into memory upon request as the data is requested. And the key here, the key to performance here is to make sure that the data format on disk and in memory are absolutely identical. So there should be no difference in the way the data is represented in memory or on disk. So we can directly map data from the disk to the in-memory format. And the architecture, the way we store the data is within pages. So it's a page-based architecture, just like most virtual memory architectures work. So let's take a closer look at the durable memory architecture. If you look at the durable memory as your total memory set, then then the way we treat it, we split it into memory regions. And memory regions are the regions where your data sets will be stored. Regions on their turn are split into segments. Segments are consecutive memory, consecutive memory space that comprises a region. So essentially, a region is unless you require it, a region will never be fully allocated. It will be allocated for initial size and then will be incremented in size of segments, and segments are consecutive memory segments. Segments on their turn are split into pages. So a page is responsible for storing all sorts of data. It may be storing index data, maybe storing metadata, maybe storing the actual data that was provided by user. And pages can be swapped to disk at any time. Essentially, probably the word swapped is wrong. Pages are stored on disk, and they can be swapped from. They can be loaded in memory at any time, and they will be served out of memory. However, if your memory fills up, and a new page is requested, a certain page will be evicted out of memory. It does not need to be moved to disk because it's already on disk. So we just toss it away from memory and load another page from disk to memory to serve the user request. So let's actually look at each individual piece on this diagram. Let's start from durable memory. As I mentioned, durable memory consumes your total space available in RAM and on disk, and has an initial size and a max size. So initial size is the initial amount of memory that will be allocated for your dataset, and then max size would be the maximum amount of memory that will be used. And once the initial dataset is filled, we will increment that memory space by the segment increments, memory segment increments. So a memory segment is a continuous physical space of memory, and a page is a fixed block that is split, a segment is split into. So a page can again be either a data page, an index page, or a metadata page. So that's actually how memory is structured. Let's look deeper at how pages work. So a page is a fixed length block. It is it uses memory very economically. It supports automatic defragmentation. So what does it mean to support automatic defragmentation? We actually have a free-list memory allocator, and I'll talk about it in a bit, which will serve pages with available consecutive free space. So if you're requesting 100 bytes and there is a page that has 100 bytes of consecutive free space, it will be served. However, if there are no pages like that, but you do have a page with 2 chunks of 50 bytes in there, Ignite will automatically defragment that page, create a consecutive 100 byte space out of those 2 50-byte chunks, and then serve it out, and then provide it for allocation. So Ignite will automatically defragment the data. So we will always attempt to utilize all the memory to its maximum. The index pages are generally B+3 pages, and we'll talk about how B+3 pages work. And method pages can be storing metadata about either index pages or about free list, like memory allocator pages. This is how a data page looks. It has a header, it has offsets on the left, and it has data on the right. The reason we've chosen that is because we can always jump from offset to data. So essentially, whenever you have to look up a certain element in a page, you look for it offset and then jump directly to its location. If we chose to store the data on the left, then offsets and data would be intermixed, and it would be very difficult to find an offset for a certain element. Here, when we actually separate them, store one on the left, another on the right, we can easily find an offset, and then offset would be a direct pointer to the data within that page, so we can immediately jump to the data that is requested. So this is how a data page looks. Now let's look at B+3 indexes. Again, it's a self-balancing tree. It works both in memory and on disk, and its main responsibility is to link and sort index pages. So B+3 indexes are always sorted. We support, as I mentioned, all sorts of indexes. We support basic hash indexes. We support sorted indexes. We support, in case of a hash indexes, it's still sorted, but it's sorted based on a hash key. We support, and hash indexes are, before I move on, hash indexes are used for direct key value lookups. So instead of actually storing key value pairs in a hash map, as most caching systems would do, Ignite actually utilizes a B+3 for hash-based lookups as well. And we also support indexes on secondary data. So all fields, all columns in your database can be indexed. We support compound indexes, group indexes. You can actually even provide hints to the system which index to use if you're using SQL. So indexes are essentially sorted, and the metadata about indexes would be stored in the metadata pages, and metadata pages actually would link these index pages together. Again, from a durable memory standpoint, the space is split into pages, and it doesn't matter what page holds. But whenever you start digging deeper, a page may be actually a data page, it can also be an index page, or it can be a memory allocator page, a free list type of page. So let's actually take a look at how at the sequence of events that happens when a certain key is accessed in Ignite. So if you issue a get on a system, on a data set, and we generally, the main API to interact with your data using key value API is cache. So Ignite cache would be a main API. You issue a get call, and you're requesting key A. So Ignite will first find the primary node where this key is stored based on its affinity function, which is supplied and started by default, and users can configure affinity, as I mentioned, to do proper collocation of data in their system. So first we find the primary node, then we will find the memory region for this key. And once we did that, we will do a lookup into B+3 within that memory region, a hash-based, so it would be a hash-based B+3. And from there, we will get to the index page, and index page may actually, at that point, may actually store the data. If your data is small, if your data is a primitive value, for example, then chances are it will be served directly out of the index page, because index page will usually cache a certain number of bytes, like first maybe 10, 20, 30 bytes of your data. And generally, if your whole data set fits into those cached bytes, then it will be served directly out of index page. If not, then it will look up the full data set out of the data page and serve the value to the user. So this is the sequence of events that generally happens. And now let's look at how free lists work, how the memory allocation works. Essentially, this is how we allocate memory whenever extra memory is requested by the system. The main responsibility of a free list is to keep essentially it's a metadata store. It's not storing the data, it's storing the data about the data. It's storing the data about the amount of free memory available within a durable memory region. And it splits it in some known predefined ranges. Can be like a list of 25% pages that are free, or about 25%, about 50%, 75%, etc. And then when a request for memory happens, free list responsibility of the free list would be to look up the closest range possible to that request and serve the available page. All right. And now I'm moving a little bit too fast. We're almost done. We're just going to look at how Ignite persistence works, how essentially the pages are mapped between memory and disk. And essentially on disk, every dataset, so if you think about Ignite, dataset in Ignite stored in different cache abstractions in Ignite, then they're mapped to disk by storing each partition in a separate file, and then having one file for all the indexes for that cache. Again, for indexes, we cannot split them by partition because Ignite generally can be started with thousands of partitions. And to do a map reduce locally in memory, across thousands of partitions is not going to be performant. So indexes actually span all the partitions. So an index file would be a file that spans that belongs to a node, not to a partition. And there is also a concept of a write-ahead log and whole archive. So what happens is every transaction Ignite will eventually end up in a write-ahead log, and then write-ahead log, when it fills up, it goes into archive, and one of the previous write-ahead logs will be reused after it's been archived. So this is essentially how the persistence architecture at a high level works. Let's actually look at the, again, sequence of events that happen when you store data in Ignite. So again, if you're doing an update, first we will be updating data in memory, and we will mark the page as dirty during the update. And then we will persist that update into the write-ahead log. The reason we don't persist directly into the storage is because inside of the storage space, it may end up, we have to actually sort it by hash keys, and it may end up not necessarily at the end of the file, it may end up in the middle of the file. And adding data anywhere other than appending data to the file, adding data anywhere other than the end of the file is expensive. And that's why we store it in a write-ahead log. We actually append it to the write-ahead log, to the end of it, and that works very fast, relatively fast. Assuming that if you use fast storage, it will work faster. If you're using fast SSDs or fast flash storage, it will work very fast. And then when a write-ahead log fills up, a certain process called checkpointing will occur. And the job of a checkpointing process is to take the pages that were persisted to write-ahead log and move them to the main storage. Note that this process does not use write-ahead log to move the pages, because the pages are still in memory. The pages were just marked dirty, but they're still in memory. So essentially, we can actually go through the memory space, memory region, scan for dirty pages, and checkpoint them into partition files, which are essentially your main storage. So why did we store it? If we don't use write-ahead log for checkpointing, why did we store it there to begin with? And the answer is to support recovery. If the system crashed after we persisted something to write-ahead log, but before we were able to checkpoint it, obviously we will lose all the memory with all the dirty copies, and then we will have to restore the data from the write-ahead log. So that's essentially the main reason why we persist data to the why we append data to the write-ahead log. Otherwise, in a normal operation, write-ahead log is never accessed. It will only be written to. It's almost never read from. And the checkpointing happens directly out of memory. And last, I will mention that there's no storage system without being able to back up and snapshot the data. And some of GridGain enterprise customers have asked us to implement backup and snapshot capabilities. So essentially, if you think about it, backup of a database is very different in a distributed system. In a distributed system, you have to take a consistent backup, a transactional backup of across all the nodes in the cluster. And every node may be a fairly large node. You can store terabytes of data. So taking a full backup periodically it may be time consuming. So GridGain supports GridGain Ultimate Edition, I should say. This is a feature of GridGain Ultimate Edition. Supports full backups and incremental backups of the data stored in Ignite. It's one of the enterprise features offered by GridGain. It also supports scheduling backups, moving backups. We call them snapshots, actually. Supports scheduling snapshots, moving snapshots around. You can actually create a snapshot in your distributed cluster and move it to a single network storage, in a single folder on the network, and restore it on a totally different cluster with a totally different size. So initially, your cluster may have been 100 nodes, but maybe you've deployed a new release of your code onto that cluster, and because of some bug, there was some discrepancy there. So you roll back to a previous snapshot, to the snapshot before the release, and you take the snapshot. No, first you take the snapshot of the latest snapshot, and then you roll back to the snapshot before the release. But because you don't probably have another 100 node cluster sitting around waiting for you to use it, you would copy that snapshot, the snapshot that you took, into a separate store and maybe start up a smaller cluster, maybe a cluster of 10 nodes or 20 nodes. With a smaller data set, maybe you don't even have to restore the whole data set on that cluster. And on that cluster, you can now analyze what went wrong offline and identify what needs to be fixed, and then roll those fixes onto the live system. So snapshots are very flexible, have a good management and monitoring capability from UI, support full and incremental snapshots, we support moving, storing it in different topologies, etc. So fairly extensive and fully managed support of snapshots and backups. And that was my last slide, and now I'll move to questions.
Great. Okay, audience, if you have any questions for Dmitry, go ahead and enter them in the questions panel. First question is, can you share the slides after the meeting? That's for me. And the answer is yes. I will send everybody a link to both the recording and the slides within 24 hours. Okay, so are there any questions for Dmitry? Just give people a couple of seconds to fill in the information. So far, there's nothing other than that one question, Dmitry. Aha, okay, here's the first question. Are you using any form of persistent memory, such as NVD, IMM, NS?
Well, so the question is does Ignite require persistent memory? The answer is no. Ignite works with regular memory. Generally, NVDM, it's non-volatile memory, works in such a way that the memory is preserved after the memory state is preserved after the cluster is restarted. But generally, that type of memory, so it's essentially memory with a special power supply. So whenever your system crashes, that memory is kept alive. When you restart it, the memory is still there. However, it requires strong support from operating systems, and not many. I haven't seen many systems that support that type of memory yet. However, Ignite is fully prepared to work with that memory, because all we need is a pointer that will map us to the place where the data was stored, and Ignite will recover on that memory and continue to operate. However, there's no requirement to use that type of memory. Ignite works with a regular DRAM or whatever other RAM you have, and the persistence is handled by the software. As I mentioned, we persist data to the write ahead log, and then checkpoint it periodically to the main storage.
Okay, next question. When will this version of Ignite be available?
So the Ignite there are two phases how the community actually is releasing this in Apache Ignite community. First phase, as I mentioned, we completely changed our architecture from on-heap based to off-heap based, and we moved it into a durable or page-based architecture. So the page-based architecture was released in 2.0. It's already out, you can play with it, and most of the SQL functionality has already been released, except for the exception of create table. So create table and persistence, together with persistence, will be released probably in 2 to 3 weeks. The way it's happening is that initially the persistence was implemented internally by GridGain for one of the customers, and then with agreement from that customer, we decided to make it open source and donate it to the community. And we did that the donation happened about beginning of May, but it takes some time for the community to absorb the code and get comfortable with it. So far it's been going well. We've done several webinars on the new functionality. We did a webinar for Apache Ignite community about how diving deeply into the code and explaining how the code works, etc. So I think we're pretty close. I think there's a thread going on a dev list actually asking exactly that, but I believe we're looking at about 2 to 3 weeks here.
Okay, next question. We are using a Hazelcast N-based solution for our biggest customer for 2 years. Is there any known replacement path to move from Hazelcast to GridGain or Ignite?
All right, that's a good question. So I'll start from saying that Hazelcast is an in-memory data grid platform. I'm assuming that's the functionality that you are using. And both Hazelcast and Ignite are implemented based on a standard. It's a JCache standard. So if most of your functionality utilizes JCache API, the transition should be fairly easy. If you go beyond a simple JCache API, then you should start looking probably at exactly how use case is supported and how, for example, a transaction is supported in Hazelcast versus how it is supported in Ignite. But most of them will be pretty similar. It's just different product, different code. The persistence piece in Hazelcast, it doesn't exist in Hazelcast. Essentially, Hazelcast, you can store data on disk just to support the fast just to restart from it, but it's just a copy of whatever is in memory. In Ignite, you can utilize Ignite as a full database, so you can store more data in Ignite than you can fit in memory. And you don't actually you are not even required to store data in memory. So the persistent piece would be brand new. So it's something that you should think about using if you do that type of migration.
Okay, next question. Is there a preference of a specific type of drive to enable off-memory storage?
Well, the faster your disk is, the faster the persistence will work. First of all, I should say that there's no requirement to have persistence. Ignite can feel very comfortable if persistence is turned off. As a matter of fact, persistence is turned off by default. By default, when you start up Ignite, it starts up as a purely in-memory system. If you turn on the persistence, then Ignite will start persisting your pages onto disk. And I would recommend using any type of flash or SSD-based storages that support high write and read throughput. Essentially, there's not a single code in Ignite that is specific to any type of storage. But the faster the storage, the faster we will be able to persist your data. This goes probably for any database, for any durable and persistent system out there. Okay. So another thing I'll mention, probably I didn't directly answer. The question actually was probably alluding to, does Ignite require any kind of commodity type of hardware with a certain type of persistent? The answer, not commodity, specific type of hardware with a certain type of persistent. The answer is no. Ignite will also run on any type of commodity hardware with any type of hard drives installed on it.
Okay, we got time for a couple more questions. What are the limitations of joins and how do you monitor and manage them?
Oh, good question. So especially important, so how do joins work in a distributed system and what are their limitations? So the main limitation, there's no limitation per se because Ignite supports both collocated and non-collocated joins. You may run into I'm not sure if you've run into an issue with maybe some very deep SQL syntax. If you did, please let us know. Theoretically, should not happen. But joins should just work, essentially. But there is a strong performance implication if you excessively use non-collocated joins. My recommendation would be avoid non-collocated joins at any cost, whenever possible. So most of the systems, you cannot fully avoid them, but if you're able to collocate about 80% of your queries, you're almost there. I mean, imagine that 80% of your queries will be lightning fast in executing under a millisecond. And then there's going to be 20% of the queries, or maybe even less if you're able to collocate more aggressively. That will work slower, and we'll have to move larger data sets around. There's no way around it in a distributed system. You either execute joins locally on each server, which are very fast, or you start moving data around, which is very slow. As a matter of fact, this is one of the differences in how Ignite, for example, SQL and Spark SQL works. Ignite provides indexes and can execute SQL queries out of utilizing indexes, primary and secondary indexes, and very fast in under a millisecond. And in Spark actually would do all the joins on all the index lookup and all the data lookups without indexes in a distributed form. So a query some queries might take minutes, like maybe 5 minutes, 10 minutes, tens of minutes in Spark. The same identical query will execute in several milliseconds in Ignite, simply because Ignite utilizes indexes and prefers collocation.
Okay, last question. If a GridGain node loses power and has data in RAM not yet persisted to disk, what is the recovery?
Can you, sorry, Alice, can you please read the question again?
Yes, if a GridGain node loses power and has data in RAM not yet persisted to disk, what is the recovery?
So the question is if the data is in RAM but not yet persisted to disk. So again, Ignite and GridGain are fully consistent systems. Whenever you commit a transaction, a commit will happen only when a data was written to the write-ahead log. It has not been checkpointed to the main storage yet, but it has been written to the write-ahead log. So if you lose your power, the data is in write-ahead log, and when you restart the system, we will scan the write-ahead log, and whenever it wasn't checkpointed, we will checkpoint into main storage before making the system available. So there will be no data loss at all. If you were writing the data to write-ahead log and haven't committed it yet, then the transaction is incomplete and will be ignored upon recovery. So you will never be in a situation where the data is lost. However, if you turn off the persistence entirely and just use a pure in-memory mode, of course, upon restart, the system will be empty and you will have to repopulate it, reinitialize it with the data.
Okay, fantastic. Well, I want to thank you, Dmitry, for a great presentation today, and also thank the audience for attending. We hope to see you on a future webinar. Please go to gridgain.com and check our schedule. We're having several really interesting topics coming up in the next couple months. So with that said, Dmitry, thank you again.
And thanks everyone for listening.
Okay, everyone have a great rest of your day. Thank you again.
Thank you. Bye-bye.